Okay, so we're going to be looking at Dalton's law and partial pressures in this PowerPoint. All gases exert a pressure. We talked a little bit about this concept in the previous unit. If you want to think about when we discussed the residual volume, which is the volume of gas that's left in your lungs no matter what, no matter how hard you exhale, you have this volume of gas that's left in your lungs, and that volume of gas exerts a pressure, and we talked about that pressure being PEEP. So that's one example of a gas that's exerting a pressure. But all gases exert a pressure. Pressure is a measure of force per unit area. I feel like that's something that conceptually we talked about in Unit 1 when you were looking at your compliance equations or your airway resistance equations, and you can start to see that as you apply pressure, you can see a volume change. It doesn't have to be volume. It could be a different measure of force, but basically it's per unit area. I feel like the easiest way to kind of link pressure in your mind is if you think about atmospheric pressure. We're all familiar with this. Most of us have flown, and if you haven't flown in an airplane, this can happen when you drive up large bluffs or a mountain. As you get higher and higher and the altitude increases, that barometric pressure decreases, and you'll usually feel that pressure change with the popping of your ears. So that's what we're talking about when we're talking about gas pressure, is that force. So the way that that's measured is with a barometer. It has 2 units of measurement that I want to talk to you guys about. It's got millimeters of mercury, so mm, and then the Hg is the periodic table name for mercury. Hg stands for mercury. Or torricelli, and that's just TORR, so torr. More commonly, you see it as the millimeters of mercury, but I don't want to say that that means that you'll never see it with torr as a unit of measurement, and it's just like all things in the medical field. We could just try to simplify and narrow everything down to one name, one acronym, one abbreviation, but what fun would that be? So I feel like the most common way you're going to see the measurements here, and then how you'll see them on my exams, are millimeters of mercury, but just in case you ever do see the torr, it is essentially the same thing. The number you'll most commonly see when you're talking about atmospheric pressure is 760 millimeters of mercury. That is the average pressure at sea level. Obviously, that can vary, and if you wanted to be really accurate, if you were doing calculations for a room, you would use a barometer. But this is a very common average number that you will see for equations, including your alveolar air equation, which I know you guys did practice and survey. So partial pressures in Dalton's law. Dalton's law says that the partial pressure of a gas should be proportional to its percentage in a gas mixture. So the proportion of pressure will be the same as the percentage of the gas in the mixture. And I know that's confusing, so I'm going to show you how that's applied. So generally speaking, when you're looking at gases, there's more than one. So like, for example, if you're looking at room air, the air that you're breathing in right now, obviously that's got oxygen in it. It also has nitrogen. It also has some random other trace gases, but it's a mixture of gases, not just one thing. The total pressure a gas mixture exerts is going to be the sum of all its individual gases. So if you're looking at room air, right, this is the example that I have down here, and you know that the air that you're breathing in right now is 21% oxygen, approximately, and 79% nitrogen, approximately, then that means that if you're looking at an average atmospheric pressure of 760 millimeters of mercury, which is what we said we're probably going to be using as your average number a lot, to figure out how much of this total pressure, how much of this total 760 is going to be oxygen, you take this 21%, or the decimal form 0.21, and you'll multiply it by the 760 to get 160 millimeters of mercury. And what that is telling us that is that of the total pressure exerted by the air in the environment, the 760, 160 millimeters of mercury of that is oxygen. If you're looking at nitrogen, the fact that that makes up 79% of the total, you would take the 0.79, which is just the decimal form of 79%, multiply that 760 millimeters of mercury, and we're getting that number as the average barometric pressure at sea level, and you're going to get 600 millimeters of mercury, and all that is 79% of 760. So kind of circling back, that shows you that the total pressure of a gas should be proportional to its percentage in a gas mixture. So it's proportional to its percentage, the percentage being 21, the percentage being 79. This is the portion of that total pressure that oxygen makes up. This is the percentage of the total pressure that the nitrogen makes up. If you then take the pressure of nitrogen, the 600, plus the pressure of oxygen, the 160, you get that total pressure of the room air mixture, the 760. And that goes to the total pressure a gas mixture exerts must be the sum of all its individual gases. So the sum of 160 and 600 equals 760. Okay, and we're going to do some more practice with this, but this is how it's applied mathematically. So barometric pressure changes based on temperature and altitude, and you can see that like some people have a barometer in their house and they watch it for the day. Depending on what the temperature is, that can increase your barometric pressure if it's warmer, decrease your barometric pressure if it's cooler. We talked about how altitude is going to affect barometric pressure. As you increase your altitude, you're going to decrease your barometric pressure. The reason that we care so much about pressure changes is that that is how your body takes in oxygen, and we'll talk about that specifically here in a second. But the fractional concentration of room air is always going to be 21%. Okay, so whether I'm breathing here or at school or at the hospital, it's 21% everywhere. So that's not changing. What can change is the barometric pressure, and that's going to affect oxygenation. Okay, so if the barometric pressure becomes, let's say, 282 millimeters of mercury, and we're trying to determine what our new pressure of oxygen is, okay? So on the previous slide, we solved our pressure of oxygen as 160 millimeters of mercury because the room air pressure was 760. Here, I'm telling you that it's 282. So your pressure of oxygen equals that 21% times 282 millimeters of mercury. That drops the pressure of oxygen down to 59 millimeters of mercury. If this would have been 760, like the average, like what it should be, you're talking about 160 millimeters of mercury. So that's a very significant drop in the pressure of oxygen. It's 1/3 of what it should be. So why do we care? The pressure of oxygen, not its percentage, will determine its physiologic activity in the body. Your body uses the pressure of oxygen as its way of oxygenating, not the percentage, okay? So just to make sure that we really have kind of locked into the pressure of oxygen versus the percentage, I'm going to have you guys pause the recording here after I get done explaining this, give it a pause, and then do the math for this slide. So for the first one, it's the barometric pressure is 456. Figure out what the pressure of oxygen is, figure out what the pressure of nitrogen is, and then move your way through it. And then when you're done, unpause my delightful recording and continue on with your lecture. But this just really kind of helps you to solidify this one concept before you move through. So this is the key. That should show you if you did the math correctly, and I just want to talk you through how that goes. The pressure of oxygen is your barometric pressure times the 21% in decimal form. Nitrogen is the same total pressure up here times 0.79, which is the 79%. If you add these together, it's about 456. Obviously, I rounded these, so it's a little bit off, but the sum of the two gases in the mixture equal the total pressure exerted by that. So practical applications of Dalton's law. Mountain climbers generally need an oxygen tank. As you increase your altitude and the barometric pressure decreases, you are going to decrease your pressure of oxygen. That means that the oxygenation of your organs and tissues will become severely compromised. That's why people take oxygen tanks up. It's why on a plane they give you the spiel about the oxygen mask when you lose cabin pressure. If you don't have enough barometric pressure to keep your PO2, which is just your pressure of oxygen, up to a safe level, you're going to start to have hypoxia of the tissues, and you're going to have difficulty oxygenating. Conversely, there are scenarios where you have higher than normal barometric pressure. I don't know how many people have heard about a hyperbaric oxygen chamber, but this is a chamber that is closed, and then they artificially increase the barometric pressures, and they can increase them to 2 to 3 times normal atmospheric pressure. So then your PO2 will become 2 to 3 times greater. We can use this for patients that have carbon monoxide poisoning, and I won't get into why that's an effective treatment right now. We'll talk a little bit more about that when we get into oxygen transport. It can be used to treat severe burn patients. So sometimes with patients that have suffered like 2nd and 3rd degree burns on their skin, the small capillaries that would normally transfer blood to the dermis have been compromised. So they have no way to oxygenate those tissues and to help them to recover, heal, and just not essentially die. So they'll put them in hyperbaric oxygen chambers, and because they increase that pressure of oxygen so much compared to the normal sea level pressure, that oxygen can actually diffuse through their tissues directly and bypass that normal circulation that it would have to undertake to oxygenate those same tissues. So they put them in there, and the pressure becomes such a difference that it can actually just diffuse directly into their skin. Which is pretty incredible when you think about the applications that can have and how much of a difference that can make for people who have gone through the tragedy of being burned in the first place, is really helping their healing and hopefully helping them to retain normal function as much as possible. So PaO2 is inversely proportional to PaCO2. When we're talking about Dalton's law and all the different individual components that make up a gas mixture and how they have to be proportional to their percentage within that mixture. The way that works in your body is you have alveoli, and within your alveoli you have alveolar pressures of gases. In your alveoli you have oxygen, you have nitrogen, because nitrogen is obviously a large component of room air, and you have carbon dioxide. And one of the things that's really important to know is if your oxygen is going up in your alveoli, then your CO2 is going down. If your CO2 is going up, your oxygen is going down. They're inversely proportional. And the reason that I kind of throw this in here now is just because as we move through this and we talk about the gases in a mixture and how you add up the sums, this is one thing that is always just going to be true. As oxygen goes up, you see the CO2 go down, and vice versa. And then I kind of put down here P equals pressure, A is alveolar, just because we start to get really acronym heavy, and so I just like to have a slide that shows you what it's standing for. You have O2, which is your oxygen, CO2, which is your carbon dioxide. Be really careful because we start talking about carbon monoxide later, so really watch that. Carbon dioxide, there's 2 oxygens here. That's the gas that you exhale. So as your alveolar oxygen goes up, your alveolar CO2 goes down. If your alveolar oxygen goes down, your alveolar CO2 goes up. This is because of Dalton's law of partial pressures. you only have 760 as your total. So if this starts taking up a larger percentage of that 760, then this is going to have to take up a smaller percentage. Okay, if this starts taking up a larger percentage of that 760, then this is going to have to take up a smaller percentage of that 760. And that's all that is saying. And as we start talking about oxygen and carbon dioxide transport, which we're going to move into in the same unit, and how your body deals with those two pressures, just remember that this is kind of where you're always going to want to circle back to. If one's going up, the other's going down. So this kind of shows those partial pressures as they move through their body. So if this is room air, the average pressure is around 160 for your oxygen, which we know because we solved that on the slide. And this is an example where this graph uses torr instead of millimeters of mercury. But if you took that 0.21 times 760, you end up with about 160 for your oxygen. And in normal air that we breathe, there's very little carbon dioxide, okay? It's a very small percentage. When you get into the trachea, which is your large airways, right, your conducting zone, you can see you still have quite a bit of oxygen, and then you're starting to get a little bit more CO2, right? When you go down to the alveoli, that oxygen's getting a little bit lower, and the reason why is if you look, this carbon dioxide is getting a little higher. And if you think about why this makes sense, your alveoli is where your gas exchange is happening. So you're attempting to drop off oxygen into the body and pick up carbon dioxide to exhale back out. So this is why these start to kind of become, this becomes much lower and this becomes much higher in the alveoli. This is where your gas exchange is happening. When you get into the tissues, you can see they start to get where the oxygen is lower than the carbon dioxide. And again, you have to think about the fact that your tissues are using this oxygen right away, right? They need it for their metabolic processes. So they're using the oxygen and they're giving off CO2, so that CO2 is getting higher. When you get into the cells, that oxygen pressure gets even lower and the CO2 gets even higher. So just kind of following this down, if you think about how our oxygenation process works, and then how our kind of waste disposal or exhalation process works, you can kind of see how this would make sense given the physiologic processes that it's going to undertake. So you start here and you work your way down. On the next couple PowerPoints, we're going to be talking in detail about how this works, how the cells pick up oxygen and carry it through the body and then pick up CO2. So we will get into like the nitty gritty of it, but just looking at how the partial pressures of oxygen decrease as you move your way through, I think is kind of helpful to understand Dalton's law and how that all kind of ties together. In survey, you guys do the alveolar air equation. This is something you're going to use a lot through this entire program. So if you haven't committed it to memory yet, please believe me when I tell you it will make your life a lot easier if you just commit it to memory now. So alveolar air equation, you're looking to solve for the pressure of alveolar oxygen, which is PaO2. This is what the equation is. You have your pressure of alveolar oxygen equals your FiO2, which is your fraction of inspired oxygen. If it's room air, it's 0.21, times your atmospheric pressure, which you're going to use 760 millimeters of mercury, unless you're given a different atmospheric pressure, which you might be. But if you're not given an atmospheric pressure, the default is 760. You're going to minus your water vapor pressure, which is always going to be 47. So you'd minus 47. Then you are going to do this separate step here where you use the PaCO2 from a blood gas. And I just want to point out that if you notice, this is the pressure of arterial CO2. And again, this gets to be a little complex, so I have these on a sheet that I will give you guys in a handout. But the capital A is alveolar, the lowercase a is arterial. So I will put all of these on I think a handout for you guys so you can try to keep them straight, because it does get to be a little bit much. P is still always going to be pressure, but this is the pressure of arterial carbon dioxide, and you get this number from an arterial blood gas. So you'd put that number here. You're going to divide it by the respiratory quotient, which is 0.08. I'm sorry, 0.8. That's always going to be 0.8, this respiratory quotient. And we'll talk a little bit more about where this comes from later. I'm going to kind of pause on that one for right now. So to do your alveolar air equation, you have to be given an FiO2, you have to be given a pressure of arterial CO2, and then you can solve. So kind of taking it through the steps, and again, I know this is something you guys did in survey. This is going to show you the steps to that equation. If you're not comfortable with this equation, please practice it. Please ask questions if you are not sure how to solve for it. What I want to draw your attention to in solving for this one is I gave you the example of 50% oxygen. And if you look, the alveolar oxygen is 300 millimeters of mercury. And why is that so high? And what I want to highlight here is that the percentage of oxygen in this gas mixture has increased from 21% to 50%. So instead of this pressure of oxygen only being 21% of the entire mixture, it is now 50% of that entire mixture. So that means it's making up a larger percentage and a larger part of that pressure. So that PaO2 is 300. It's higher than it would normally be if it was just room air, which is at 21%. So you can see how with altering your FiO2 or altering your barometric pressure, you can start to see a real difference in the pressure of oxygen. And we'll talk about all the different applications for that as we move through. But this is just kind of the intro to get you comfortable with some of the terminology and reintroduce you to this alveolar air equation. So kind of dig into this and practice the math if it's something you don't feel comfortable with. For your lecture questions, I'm going to have you just keep practicing that math. So what is the PaO2? So what is the alveolar pressure of oxygen with an FiO2 of 60% and our arterial CO2 of 30? So you'd use your alveolar air equation for this one. What is the pressure of oxygen of 50% at a barometric pressure of 700? So that's going to be where you just multiply them together. What happens if the barometric pressure, what happens to the barometric pressure as your altitude increases? What effect will that have on oxygenation and why? And then I have it the other way in the hyperbaric chamber. So take some time to answer those. If you have any questions, as always, please email me. I do want to say that because we're starting to get into a lot more math and concept-driven things, when we meet for our review on Thursday, have some questions prepared. If not, I'm going to probably start doing just mini lectures in the beginning where I go over things that I think potentially might not have landed or are a little bit more complex. So I don't want you guys to panic if when you listen to my recording, you have no idea what I'm talking about. There will be space to answer questions and to go through it together. And I always want you guys to feel comfortable knowing that is the goal of those Tuesday, Thursday meets, is that we can really clarify any confusion that you have from just listening to my lectures and looking at them on your own. I think if we don't start utilizing that time and people potentially being more comfortable asking questions earlier on, I do think it's going to get challenging in the learning process. So just kind of be aware that I will answer and take whatever time you guys need, but you have to meet me halfway and tell me what I can help you do or what you're not understanding. And that is it.